The GPS mystery. Let's look at a system we use every day. Here is Earth, and orbiting high above is one of the satellites that helps us navigate. As it glides through space, notice how its internal clock behaves differently than ours. It turns out that GPS clocks tick faster in space, gaining about 38 microseconds every single day. Now, that might sound like a tiny discrepancy, but if we ignored relativity, the results would be disastrous. Watch as this car attempts to find its intended position. Without Einstein's corrections, the timing error accumulates so fast that within a day, your GPS would be off by 10 kilometers, leaving you completely lost. Let's explore the idea of a universal constant. In our everyday world, speeds are additive. Watch as this person moves along the number line. By throwing a ball forward, their individual speeds combine. 10 plus 20 gives us 30. It's intuitive, simple addition. But under Einstein's special rule, the math changes. Imagine a train traveling at 80% the speed of light. If it shines a beam forward, you might expect the speeds to stack. However, as the photon moves, we see that 0.8 c plus c is still just c. Light speed is constant for everyone, no matter how fast they are moving. This is the fundamental bedrock of relativity. To understand time dilation, let's look at the classic light clock. In Alice's frame, she's at rest. A photon bounces vertically between two mirrors, separated by a distance L. Since light moves at a constant speed c, the time for one tick is simply L over c. It's a straightforward vertical trip. Now, watch what happens from Bob's perspective as Alice moves past him. Because the clock is moving, the photon must follow a diagonal path to keep up with the mirrors. Compare this zigzag to the original vertical path shown by the dashed line. The photon is clearly traveling a greater distance. Since the speed of light is constant for all observers, light takes longer to complete this longer journey. This means Bob sees Alice's clock ticking slower, revealing the beautiful reality that time itself is relative. Let's translate this geometry into the formal language of mathematics. As the right-angled triangle forms, it captures the essence of our two perspectives. Notice the labels appearing. The vertical leg is the fixed height of the clock from Alice's view, while the base represents the horizontal distance the ship covers at velocity v, according to Bob. The hypotenuse marks the total diagonal distance light travels in Bob's frame. Because this is a right triangle, we can use the Pythagorean theorem to relate these distances. Starting with the square of the hypotenuse, we begin to rearrange the terms. Watch how we move the velocity term to the left to group Bob's time measurements together. By factoring out his time interval and simplifying, we isolate the relationship between the two observers. Finally, we take the square root to arrive at the time dilation equation. This golden box highlights one of the most profound realizations in physics. Time is not absolute, but relative to your motion through space. Let's look at how extreme speeds distort reality, starting with time dilation. On the left, Bob's clock is stationary, while on the right, Alice travels at 80% the speed of light. As the hands spin, notice the discrepancy. Bob's clock ticks normally, but Alice's clock lags behind, moving significantly slower. Time literally stretches for the moving traveler, but space distorts too. Consider this train car. At rest, it measures 100 meters, but as it reaches relativistic speeds, watch how it physically compresses. It shrinks to just 60 meters. This contraction of space is how the universe ensures the speed of light remains constant for everyone, regardless of their motion. We begin with a grid representing the stage of our universe. Notice the key takeaway. Space and time are not separate entities, but one single fabric. Watch as the grid begins to ripple and curve. This warping is the fundamental nature of the universe. This is space-time. This isn't just abstract theory, though. Look at the satellite in the corner. Without Einstein's insights into how gravity and motion affect time, your GPS would be miles off. His logic is what keeps your location accurate to within just a few meters.